So this is the second video for the IR part 3 through 7 worksheet, so this will go over the first 3 free response questions. So number 8, indicate which CN stretching mode absorbs the higher frequency IR photon explained by using Hooke's law. So first let's look at the two molecules. So this first one has a nitrogen double bonded to a carbon, and this one has a nitrogen single bonded to the carbon. So we know Hooke's law is based on that spring constant over mass equals the frequency. So for the spring constant, the tighter and the stronger the spring, the higher the frequency. So for a double bond, that would be a tighter spring than the single bond. So that would mean it would have a bigger K. So it would be greater than this one's K. So that would also lead it to have a higher frequency. So this one has a higher frequency. So now for number 9, indicate which CN stretching mode absorbs the higher frequency IR photon explained by using Hooke's law. So this is the same question from before, but now we have a different example. So the only difference between these two molecules is that this one uses an isotope of carbon, so that's carbon 13, and this one uses our standard carbon 12. So in terms of this now we'll be looking at the mass portion of Hooke's law. So before we were looking at K, and now we'll be focusing on this M. So the C13 has a bigger M than the second one. So whereas we were increasing the top of the fraction before, this time we're increasing this mass on the bottom. So the larger the denominator of a fraction is, the smaller the frequency would be. So because this carbon 12 has a smaller mass, its denominator is smaller, and you would end up with a higher frequency. So this is our higher frequency photon. So now for the last question, number 10. Based on the intensities of the carbon-carbon double bond stretching bands, match each of the compounds here with its IR spectrum and explain your choice. So first let's look at the two molecules. So on the left we have methylcyclohexane, and on the right we have 1-methylcyclohexene. So one important thing when we look at the two molecules is to consider how symmetric they are about the double bond. So for this first one, we have H, H, and then down here, these are technically R groups, even though they're both connected to the same ring, with this double bond in the middle. And then on the right, we have we're actually looking right here. So we have R and R, the double bond, and then R and H. So here we have complete different halves, and here we have a half that's kind of similar to the other. So this 1-methylcyclohexene is more symmetrical. And then this one would be less. So based on that symmetry, we would then look at the intensity of the peak around 1600. So we're looking here, these should be around 1650. And we see the one on the right is much more intense than on the left. So that one would correspond to the molecule that's less symmetrical. So this would go here, and then the 1-methylcyclohexene would be over here. And that's based purely on this symmetry and the intensity of the peaks. So the more intense the peak is, the less symmetrical the molecule would be, specifically in reference to the double bond in this case. So that's about it for this one. If you have any other questions or want more explanations, feel free to reach out. I can maybe discuss like what you did for this question or any of the other ones.